In this lecture, we'll consider an example of differential equations. In particular, I'll show you the situation involving a mass spring system. And then we'll talk about Cauchy Euler equations. Let's consider a situation where we have a spring.
Wait, can you restart? Go ahead.
Let's consider a situation where we have a spring and a mass in the form of a ball, let's say, attached to that spring. Okay? If we don't do anything to the spring or the mass, the system is in the resting position, which we call where we have y equals 0, and y represents the position of the ball. Now imagine we pull the ball down and then release. Then the spring will contract and expand, contract and expand. So what we want to do is determine what is the position of the ball at any given time. Okay? So y would represent the position of the ball at time t. Position of the mass. And we want to know what's the position of the mass. In this case, we assume that the system is undamped. All right. So we have a couple of physics equations related to this situation. The first one is Hooke's law, and the Hooke's law says that the force acting on the system is equal to negative k times y, where again y was the position of the ball, and k is a constant which represents the stiffness of the spring. Another law that we need is Newton's second law, which says that force is equal to mass times acceleration. Now you know that acceleration is the second derivative of the position of the object. So we have two equations, F equals minus k times y and F equals m times y double prime for force. Since they both represent force, they must be equal to each other. So we get that m y double prime must be equal to negative ky. Let's move ky term to the left side, and we'll get equation my double prime plus ky equals 0. And if we can solve this equation, we will figure out the equation for y. And this is a differential equation. Notice this is a second order differential equation with constant coefficients. And we've talked about how to solve these types of equations. Let's try to solve it. Or maybe we can take a second and you try to solve it first. So let's try to solve that equation. We will divide by m. And if we divide by m, we get y double prime plus k over m y equals 0. Remember, the first step in solving a second order homogeneous equation with constant coefficients, the first step is to solve the characteristic equation. So in this case, the characteristic equation is lambda squared. Now notice there's no y prime, so there will be no lambda here. We'll just have plus k over m equals 0. This is the characteristic equation. So to solve it, I move negative km to the other side. Then I take square roots. I get plus minus square root of negative k over m, which I can write as plus minus square root of km. And if I take the negative from under the square root, it turns into I. So the solution of the quadratic equation is a complex number. And this is case 3, if you remember. In this case, alpha, the real part of the solution, is 0. And beta, the imaginary part, is square root of k over m. So recall that in this case, the solution was in the form e to the power alpha t c1 cosine beta t plus c2 sine beta t. Okay? And in our case, alpha is equal to 0. So if I put 0 here, e to the power 0 would be 1. So we don't have to write it. This term is 1. And beta is equal to square root of k over m. So what we get is c1 cosine square root of k over m t plus c2 sine square root of k over m t. So that's our solution. So this is one application of second order homogeneous equations with constant coefficients. Now let's talk about Cauchy-Euler equations. So a Cauchy-Euler equation is any equation that can be written in this form. So what's so special about this form? Notice that if we have y double prime, then there must be an x squared. And if there's y prime, there must be an x next to it. And then the y is just by itself. So any equation that can be written in this form is called a Cauchy-Euler equation. To solve this equation, we'll start with the following. Let's suppose that we know that the solution is of the form y equals x to the power m. Okay, so we know the solution has to be x to the power m. And what we have to do is figure out what is the value of m. So let's think about it. Well, if x to the m is the solution of the differential equation, it has to satisfy the differential equation. So if I plug x to the m into the equation, the left-hand side has to be equal to the right-hand side. So let's try to do that. Let's plug in x to the m into the equation and see what happens. All right, so if y equals x to the m, then y prime would be equal to m x to the m minus 1, and y double prime would be equal to m times m minus 1 x to the m minus 2. So let's plug in everything into the Cauchy-Euler equation. So what do we get? We have x squared times y double prime, which in our case is m times m minus 1 x to the m minus 2. So this is y double prime plus ax times y prime, and y prime is equal to m x to the m minus 1 plus by. And this must be equal to 0. Okay, let's simplify the left-hand side. So on the left-hand side, we get x squared times x to the m minus 2 would be just x to the m, because I just add the exponents. So if I add 2 with m minus 2, I just get m, because 2 and minus 2 cancel. And then I have m minus 1. Down here, if I multiply x with x to the m minus 1, again, I would be adding the exponents, and that would give me x to the m again. And I have a and m. And over here, oops, let's write, instead of y, let's write x to the m. Now, notice that this term has x to the m, this term has x to the m, and this term has x to the m. Let's factor out x to the m. So if I factor out x to the m, I'll get m times m minus 1 plus am plus b. And that has to be equal to 0. So if I have a product of two terms, so here's one term, here's another term, this times this has to be equal to 0, then either the first term must be equal to 0 or the second one. Setting the first term equal to 0 won't produce any meaningful results. But if I set the second term equal to 0, then that would help us. So what we get is that m times m minus 1 plus am plus b, this must be equal to 0. So whatever is m, it has to satisfy this equation. And this is what we call a characteristic equation. This is our characteristic equation. Oops. This is the characteristic equation of the Cauchy-Euler equation. So when you encounter a Cauchy-Euler equation, you know the solution has to be of the form x to the m. To find m, we need to solve the characteristic equation. So the first thing you do when you see a Cauchy-Euler equation is solve the characteristic equation. That's the first step. Step number 1, always do that. All right, let's look at the example. So when we solve this characteristic equation, because this is a quadratic equation, there are 3 things that can happen in terms of the roots of this quadratic equation. The first case is when you get 2 real roots which are distinct. So case 1 is when we get 2 distinct real roots. So let's call them m equals m1 and m equals m2. These are 2 solutions of the characteristic equation. Then in this case, the solution of the differential equation will be c1 x to the power m1 plus c2 x to the power m2. So if you remember, this is very similar to what we did with second order differential equations with constant coefficients. We had 3 cases, and for each case we had a special solution. All right, now let's look at an example. Suppose we're given equation x squared y double prime plus 1.5x y prime minus 0.5y equals 0. Why don't you take a second and see if you can solve this equation on your own? Okay, let's try it together. So this is a Cauchy-Euler equation. And we said the first step to solve a Cauchy-Euler equation is to solve its characteristic equation. So in this case, our equation is going to be m times m minus 1 plus am. This is a, so we get 1.5m plus b. b is negative 0.5. So that's our characteristic equation. Let's simplify it a little bit. If I multiply by m, I'll get m squared minus m plus 1.5m negative 0.5. Minus m plus 1.5m gives us plus 0.5m. So this is a quadratic equation. Notice this is a quadratic equation. Let's try to factor it. So how can we factor it? Let's try m plus 1 and m minus 0.5. Let's think for a second if this is going to work. I believe it's going to work. So we'll get 2 solutions. First root would be minus 1. And the second root would be plus 0.5. So we have 2 distinct real solutions therefore our solution of the differential equation is going to be, according to this formula, C1 x to the power -1 plus C2 x to the power 0.5. So it's very straightforward, and we're done. Let me do another example. Case 2, when you solve the characteristic equation, is you get 2 repeated solutions. Case 2, we have 2 repeated solutions. And M1 equals M2. So when that happens, when you get repeated solutions, then the solution of the differential equation is going to be y equals C1 x to the power m plus C2 times ln x times x to the power m. Let's look at an example. Let's say you're asked to solve this equation. Why don't you take a second and see if you can solve it on your own. Okay, let's try it together. This is a Cauchy Euler equation. So the first step is to solve the characteristic equation. So we have m times m minus 1. A is minus 5, so it's minus 5m plus b, which is 9. Let's simplify this. M times m is m squared. M times minus 1 is minus m. Minus 5m together is minus 6m plus 9. So this factors as m minus 3 times m minus 3. So we get 2 solutions, m equals 3 and m equals 3. So this is the case when I have repeated solutions. So then the solution of the original differential equation will be given by this formula. So what I get is C1 x to the power 3, C2 ln x times x to the power 3. Again, very straightforward. So I'll just do one more example. I'll finish. Let's consider the next example. Why don't you take a second and see if you can solve it on your own. All right, let's try it together. So notice that we have a Cauchy Euler equation. So we start by solving the characteristic equation. So the characteristic equation would be m times m minus 1 minus 4m plus 6. So if I simplify, m times m is m squared. M times minus 1 is minus m. With minus 4 gives us minus 5m plus 6 equals 0. So let's try to factor it. It would be m minus 2, m minus 3. So that gives us 2 solutions. m1 equals 2 and m2 equals 3. This is case 1 when I get 2 real distinct solutions. So once we get the general solution, we can find the constants C1 and C2 using the additional information. So let's try to do that. Notice we also would need y prime. So let's compute y prime. So if I take the derivative, I'd get c1 times 2x plus c2 times 3x squared. All right. Now, we know that y of 1 equals 0.4. So that means if I replace x with 1 and y with 0.4 in this equation, I would get 0.4 equals c1. Remember, I have to put 1 instead of x. 1 squared is just 1, so I don't have to write it. And then 1 cubed is also 1, so 1 times c2 is just c2. Next, we know that y prime of 1 is equal to 0. So I'll replace y prime with 0 and x with 1. That would give me 0 equals, if I put 1 here, I'd get 2c1. And if I put 1 here, I get 3c2. So I have two equations and two unknowns, c1 and c2. It's a system of equations. I can solve it. So what I can do is, from the second equation, I can solve for c1. So move this term to the other side and divide by 2. So we get c1 has to be equal to minus 3 over 2c2. And replace this c1 with minus 3 over 2c2. And I'll get, so down here, 0.4 equals minus 3 over 2 c2 plus c2. Minus 3 over 2 plus 1 is equal to minus 1 over 2. So if I multiply both sides by minus 2, I'd get that c2 is equal to minus 0.8. And if c2 equals minus 0.8, I plug it in here, and I get c1 is equal to 1.2. Okay? So we found c1 and c2, and we'll replace c1 and c2 in our general solution. So we get y equals 1.2 x squared minus 0.8 x cubed. So that's our final answer.